Imagine a structure so vast that light itself takes 100,000 years to cross from one edge to the other. A disk of stars rotating through space, turning once every few hundred million years, each revolution marking what we might call a single breath of cosmic time. These are spiral galaxies, and they exist in their billions throughout the observable universe, each one a slowly spinning island containing hundreds of billions of stars, gas clouds larger than solar systems, and dust lanes that trace elegant curves through the darkness of space. About 60% of all galaxies observed by astronomers show this spiral structure. This means that most stars in the universe, including our own Sun, reside within galaxies that possess these distinctive arms curving outward from a central region. The spiral form appears again and again across cosmic distances, from galaxies just a few million light-years away to those whose light has traveled for billions of years to reach our telescopes. The spiral galaxy is not an exception in the cosmos, but rather a fundamental expression of how matter organizes itself under the influence of gravity and rotation. The arms themselves appear bright against the darker disk between them, glowing with the light of newly formed stars. These young stars burn with intense blue-white light, creating a visual signature that allows us to trace the spiral pattern even when observing galaxies from millions or billions of light-years away. Between the arms, older stars continue their orbits, contributing to the overall glow of the galaxy, but lacking the brilliant luminosity of their younger counterparts in the arms. This difference in brightness creates the spiral pattern we observe, a contrast between the densely populated stellar nurseries of the arms and the more evenly distributed older population throughout the disk. The central bulge of most spiral galaxies appears different from the arms, often glowing with a yellow or reddish hue rather than the blue of the spiral arms. This color difference reflects the ages of stellar populations within each region. The bulge contains stars that formed billions of years ago during the early assembly of the galaxy, while the arms host stars that may be only a few million years old, newly condensed from clouds of molecular hydrogen and helium. This temporal stratification means that a single spiral galaxy contains stars spanning nearly the entire age of the universe, from those born in the galaxy's youth to those forming at this present moment. Most spiral galaxies rotate as cohesive structures, their disks turning around central points that typically harbor supermassive black holes. These black holes, despite their tremendous masses, often millions to billions of times the mass of our Sun, occupy volumes smaller than our solar system. The gravitational influence of these central black holes extends throughout the galaxy, but it is the collective gravity of all the galaxy's stars, gas, and unseen dark matter that determines the orbital paths of individual stars. Each star follows an elliptical path through the galactic disk, sometimes passing through spiral arms, sometimes traveling through the spaces between them. The time required for a star to complete one orbit around the galactic center depends on its distance from that center. Stars closer to the core complete their circuits faster, while those farther out take longer. In our own Milky Way, the Sun orbits at a distance of approximately 26,000 light-years from the center, traveling at a speed near 230 kilometers per second. At this velocity and distance, the Sun requires approximately 225 million years to complete one full orbit, a span of time known as a galactic year. Since the Sun formed about 4.5 billion years ago, it has completed roughly 20 orbits around the galactic center. The mechanisms that create and maintain spiral arms have puzzled astronomers for decades. If the arms were simply groups of stars moving together through space, the differential rotation of the galaxy would wind them tighter and tighter over time, eventually causing them to vanish. But observations show that spiral arms persist for billions of years, maintaining their structure across many galactic rotations. The prevailing explanation involves density waves, regions of slightly higher density, that rotate through the galactic disk at a speed different from the stars themselves. As stars and gas clouds pass through these density waves, they experience increased gravitational forces that can trigger star formation and cause the brightening we observe as spiral arms. In this way, the spiral arms are not fixed collections of stars, but rather patterns that persist even as individual stars move through them. A star born in a spiral arm will eventually drift out of that arm, continuing its orbit through quieter regions of the disk, while new stars form in the arm behind it. This creates a kind of cosmic traffic pattern, with stars entering and leaving the arms throughout their lifetimes. The arms themselves rotate at a speed different from the stars, meaning that the pattern speed and the stellar orbital speeds are distinct quantities. This separation allows the spiral structure to persist without winding up over time. Observations across different wavelengths reveal various aspects of spiral galaxy structure. In visible light, the bright blue stars of the spiral arms dominate, creating the familiar spiral pattern. In infrared wavelengths, the overall distribution of older stars becomes more apparent, along with dust that absorbs visible light and re-radiates it in the infrared. Radio observations can detect neutral hydrogen gas throughout the disk, revealing the raw material for future star formation. X-ray observations sometimes reveal hot gas near the galactic center or the remnants of supernova explosions throughout the disk. Each wavelength provides a different perspective on the same galactic structure, building a comprehensive picture of how these systems function. The discovery that most stars in spiral galaxies orbit at roughly constant speeds, regardless of their distance from the galactic center, provided some of the first compelling evidence for dark matter. According to Newtonian physics, if visible matter were the only mass present, stars farther from the center should orbit more slowly, much as outer planets in our solar system take longer to complete their orbits than inner planets. However, observations revealed that rotation curves remain relatively flat far beyond the visible edges of spiral galaxies, implying the presence of substantial amounts of unseen matter extending well beyond the visible disk. This dark matter appears to form extended halos around spiral galaxies, contributing most of the galaxy's total mass despite remaining invisible to our telescopes. These systems exist on scales that challenge human comprehension. A typical spiral galaxy might measure 100,000 light-years across its visible disk, meaning that light from one edge requires 100,000 years to reach the opposite edge. Within this volume, hundreds of billions of stars follow their individual orbits, while clouds of molecular hydrogen spanning tens or hundreds of light-years drift through the disk. Dust particles, each smaller than a grain of sand, collectively form lanes and patches visible across thousands of light-years. And, pervading everything, dark matter provides the gravitational framework that holds the entire structure together. We are going to explore spiral galaxies together, moving through their various features at a pace that allows us to appreciate the quiet enormity of these structures. There will be no rush, no urgency, only a steady progression through the facts and observations that astronomers have gathered over decades of study. The journey will take us from the broad outlines of spiral structure to the specific details of star formation, rotation, color, and scale, building a comprehensive understanding piece by piece. Along the way, we will encounter numbers that represent vast distances and immense timescales, quantities that exist far beyond everyday human experience. These numbers are not meant to overwhelm, but rather to provide precise descriptions of phenomena that unfold across light years and millions of years. When we say that a spiral galaxy extends 100,000 light-years across, we are stating a measured fact about physical space, a distance that light, traveling at 300,000 kilometers per second, requires 100,000 years to traverse. Such numbers ground our understanding in observable reality. The tone will remain calm and steady throughout. There will be no dramatic revelations, no sudden shifts in subject or intensity, only a measured exploration of what spiral galaxies are and how they function. If you find yourself drifting into sleep, that is perfectly acceptable. The information will continue at the same even pace, allowing you to engage as deeply or as lightly as feels comfortable. The purpose here is not to demand attention, but to provide a gentle framework for rest while offering genuine astronomical knowledge to those who wish to follow along. Spiral galaxies have existed for billions of years, their structures forming when the universe was younger and less evolved. Many of the spirals we observe today assembled their basic structure when the cosmos was perhaps a third of its current age, though they have continued to evolve since then through star formation, minor mergers with smaller galaxies, and the gradual redistribution of gas and stars. This means that spiral galaxies are mature systems, not transient phenomena, and their current properties reflect billions of years of gradual evolution under the consistent laws of gravity and gas dynamics. The study of these galaxies combines observations across the electromagnetic spectrum with theoretical models of how gas, stars, and dark matter interact under gravitational forces. Astronomers observe spiral galaxies at many different distances, seeing them as they existed at various times in cosmic history. By comparing nearby spirals, whose light left them just a few million years ago, with distant spirals, whose light began its journey billions of years ago, researchers can piece together how these structures have changed over cosmic time. This comparative method has revealed that spiral galaxies were once less common than they are today, and that the proportion of barred spirals has increased as the universe has aged. The disk of a spiral galaxy is remarkably thin compared to its diameter, with a typical thickness of perhaps 1,000 light-years compared to a diameter of 100,000 light-years. This gives the disk an aspect ratio similar to that of a compact disk, very flat relative to its extent. Stars within the disk follow orbits that keep them close to the galactic midplane, oscillating above and below this plane with a period of tens of millions of years, but never straying far from it. This confinement to a narrow vertical range creates the thin disk structure visible when we observe spiral galaxies edge on from our perspective on Earth. Gas within the disk also concentrates near the midplane, particularly the cold molecular gas that forms stars. This gas exists primarily in discrete clouds rather than being uniformly distributed, with individual clouds ranging from a few light-years to several hundred light-years in diameter. The largest of these clouds, the giant molecular clouds, contain enough material to form thousands or even hundreds of thousands of stars. These clouds are densest in the spiral arms, where the compression from density waves increases the likelihood of gravitational collapse and subsequent star formation. The process of learning about spiral galaxies is itself a kind of journey through accumulated evidence, each observation adding to the overall picture. Early observations with simple telescopes revealed only the gross structure of nearby spirals, their arms appearing as faint wisps of light surrounding brighter central regions. As telescopes improved and photographic techniques developed, more detail emerged, revealing the complexity within the arms, the presence of dark dust lanes, and the variations in structure from one galaxy to another. Spectroscopy allowed astronomers to measure rotation curves and determine that galaxy's spin. Radio astronomy revealed the distribution of neutral hydrogen. Each advance in technique refined our understanding while confirming the basic reality that spiral galaxies are rotating disks of stars and gas organized into spiral patterns. This accumulation of knowledge continues today, with modern telescopes like the Hubble Space Telescope, the James Webb Space Telescope, and various ground-based observatories capturing images and spectra of spiral galaxies in unprecedented detail. We can now resolve individual star-forming regions in galaxies millions of light-years away, measure the motions of gas clouds near galactic centers to determine black hole masses, and trace the distribution of dark matter through careful analysis of rotation curves. These observational capabilities have transformed spiral galaxies from mysterious spiral nebulae into well-characterized systems whose basic properties and evolutionary patterns are reasonably well understood, though many details remain to be worked out. What follows is an exploration of these well-characterized properties, presented in a manner intended to be both informative and conducive to rest. We will move through structure, star formation, color, rotation, scale, central regions, and variations, building a complete picture of what spiral galaxies are and how they exist in the universe. Each section will flow into the next without abrupt transitions, maintaining a steady rhythm designed to allow either active engagement or gradual drift towards sleep. A spiral galaxy possesses several defining features that distinguish it from other galaxy types. The most obvious is the presence of spiral arms, curved structures that extend outward from a central region and wind through the disk of the galaxy. These arms are not arbitrary designations, but rather observable concentrations of bright young stars, gas, and dust that trace logarithmic spirals through the galactic plane. The number of arms varies from galaxy to galaxy, with some displaying two prominent arms in a grand design pattern, while others show multiple, more fragmentary arms in what astronomers call a flocculent structure. The central bulge forms another key component, appearing as a roughly spherical or ellipsoidal concentration of stars near the galactic center. This bulge typically glows with the combined light of billions of older stars, creating a yellowish or reddish hue distinct from the blue tint of the spiral arms. The bulge may be small, relative to the disk in late-type spirals, or quite substantial in early-type spirals, with the bulge-to-disk ratio serving as one criterion for classifying spiral galaxies along the Hubble sequence. In our own Milky Way, the central bulge extends approximately 10,000 light-years from the galactic center. Surrounding both the disk and bulge is the galactic halo, a roughly spherical region containing old stars, globular clusters, and substantial amounts of dark matter. The halo stars are typically metal-poor compared to disk stars, meaning they contain lower abundances of elements heavier than hydrogen and helium. This chemical difference indicates that halo stars formed early in the galaxy's history, before multiple generations of stars had time to enrich the interstellar medium with heavy elements produced through nuclear fusion and dispersed in supernova explosions. The halo extends far beyond the visible disk, with some globular clusters orbiting at distances of several 100,000 light-years from the galactic center. The disk itself, where the spiral arms reside, can be divided into a thin disk and a thick disk. The thin disk contains the youngest stars, including those currently forming in molecular clouds, along with most of the galaxy's remaining gas. This component is only about 1,000 light-years thick near the Sun's location in the Milky Way. The thick disk contains somewhat older stars and extends to roughly 3,000 light-years in thickness. Stars in the thick disk have higher velocity dispersions, meaning they move with more random velocities relative to the smooth circular motion that characterizes the thin disk. This suggests that the thick disk formed through different processes than the thin disk, possibly involving early merger, events, or dynamical heating from interactions with satellite galaxies. Most spiral galaxies also contain a bar-shaped structure extending through their centers, with spiral arms emerging from the ends of this bar rather than from a circular bulge. Approximately 2/3 of all spiral galaxies show evidence of such bars, though the strength and length of bars vary considerably. The Milky Way possesses a modest bar structure, roughly 27,000 light-years in length, though this feature is difficult to observe directly from our position within the galaxy. Bars form through gravitational instabilities in the disk and can significantly affect the dynamics of gas and stars in the inner regions of the galaxy, funneling material toward the center and influencing star formation patterns. The classification of spiral galaxies follows schemes developed primarily by Edwin Hubble in the early 20th century and refined by later astronomers. Hubble divided spirals into types SA, SB, and SC based on the tightness of their spiral arms and the size of their central bulges. SA galaxies possess tightly wound arms and large bulges, while SC galaxies show loosely wound arms and small bulges, with SB galaxies falling between these extremes. A parallel sequence classifies barred spirals as SBA, SBB, and SBC, following similar criteria. Later refinements added types SD and beyond to account for very late-type spirals with minimal bulges and very loose, fragmented arms. Our own galaxy, the Milky Way, serves as a crucial reference point for understanding spiral galaxies, as it is the only one we can study from within. This inside perspective allows extremely detailed observations of individual stars, gas clouds, and dust structures that would be impossible to resolve in external galaxies millions of light-years away. However, this same inside perspective makes it difficult to determine the overall structure of the Milky Way, as we cannot step outside to view it face-on. Astronomers must instead piece together the galactic structure through careful mapping of stellar positions, gas distributions, and kinematic measurements of how stars and gas move throughout the disk. These observations have revealed that the Milky Way is a barred spiral galaxy with a diameter of approximately 100,000 light-years and a disk thickness of about 1,000 light-years near the Sun's position. The Sun orbits at a distance of roughly 26,000 light-years from the galactic center, moving through a region sometimes called the Orion Spur, a minor arm or feature between the larger Sagittarius and Perseus arms. The galaxy contains at least 100 billion stars, possibly several times that number, along with vast amounts of gas, dust, and dark matter. The total mass, including dark matter, is estimated at roughly 1 trillion times the mass of the Sun. The chemical composition of stars provides insight into the history of spiral galaxies. The oldest stars in the halo contain very low abundances of elements heavier than helium, indicating they formed from primordial material that had not yet been enriched by stellar nucleosynthesis. Stars in the disk show progressively higher metallicities, reflecting the gradual enrichment of the interstellar medium as successive generations of stars produced heavy elements through nuclear fusion and distributed them via stellar winds and supernova explosions. The youngest stars forming today in molecular clouds have the highest metallicities, containing oxygen, carbon, nitrogen, iron, and other heavy elements that did not exist when the first stars formed. The presence of substantial amounts of cold gas in spiral galaxy disks distinguishes them from elliptical galaxies, which typically contain very little gas and show minimal current star formation. This gas content, particularly molecular hydrogen, ensures that spiral galaxies continue to form new stars at appreciable rates, billions of years after their initial assembly. The Milky Way currently converts roughly 1 to 3 solar masses of gas into stars each year, a modest rate compared to starburst galaxies, but sufficient to maintain a population of young, luminous stars in the spiral arms. This ongoing star formation gives spiral galaxies their characteristic blue colors in regions where young stars are present. The flat, rotating disk structure of spiral galaxies arises naturally from the collapse of rotating clouds of gas in the early universe. As a protogalactic cloud contracts under its own gravity, conservation of angular momentum causes it to spin faster, much as a figure skater spins faster when pulling in their arms. Material falling toward the rotation axis is deflected by centrifugal forces, causing it to settle into a disk perpendicular to the rotation axis rather than falling directly toward the center. This process, repeated countless times throughout the universe, produces the multitude of galaxies we observe today. The stability of these disks over billions of years demonstrates that spiral galaxies are not transient structures, but rather long-lived configurations that persist through numerous rotations. The gravitational forces within the disk, combined with the pressure provided by stellar orbits and gas dynamics, maintain the disk against perturbations that might otherwise disturb its structure. Minor mergers with small satellite galaxies can inject energy into the disk and create temporary disturbances, but the disk typically settles back into a stable configuration over timescales of hundreds of millions of years. Understanding what defines a spiral galaxy requires recognition that these are complex multi-component systems where different regions have different properties and histories. The bulge, disk, halo, and dark matter halo each contribute to the overall structure and dynamics, and each component tells part of the story of how the galaxy formed and evolved. The spiral arms themselves, while visually striking, represent just one aspect of these systems, overlaid on a disk that would exist even without the prominent spiral pattern. This multi-layered nature means that a complete description of a spiral galaxy must account for stellar populations of various ages, gas in multiple phases, dust that obscures and scatters light, and the dark matter that dominates the total mass despite remaining invisible to our telescopes. Spiral arms represent concentrations of bright young stars, gas, and dust that trace curved paths through galactic disks. The arms are not solid structures, but rather density enhancements where material temporarily accumulates as it orbits the galactic center. This distinction is crucial for understanding how spiral arms can persist for billions of years despite the differential rotation that would otherwise wind them up into ever tighter spirals. The density wave theory, developed primarily by C.C. Lin and Frank Hsu in the 1960s, provides the theoretical framework for understanding this persistence. According to density wave theory, spiral arms are regions where the density of stars and gas is higher than average, analogous to traffic jams on a highway. Just as cars enter and leave a traffic jam while the jam itself persists in one location, stars and gas clouds enter and leave spiral arms while the arms themselves maintain their positions relative to the galactic center. The arms rotate at a pattern speed that differs from the orbital speeds of stars and gas, creating a dynamic where material streams through the arms at varying rates depending on its distance from the galactic center. As gas enters a spiral arm, it encounters the increased gravitational force from the enhanced density in the arm. This causes the gas to slow down slightly and compress, increasing its density further. The compression can trigger gravitational collapse in molecular clouds, leading to the formation of new stars. Many of these new stars are massive and luminous, shining with intense blue-white light that makes the spiral arms appear bright against the dimmer background disk. The brightest of these stars have main sequence lifetimes of only a few million years, meaning they live and die without ever leaving the spiral arm where they formed. Their brief lifetimes ensure that the spiral arms remain prominently highlighted by blue light, even though the arms themselves are not composed of a fixed population of stars. The formation of spiral arms can be triggered by several mechanisms. Internal gravitational instabilities within the disk can spontaneously generate spiral patterns under the right conditions. The influence of a nearby companion galaxy can also drive spiral structure through tidal forces that disturb the disk. Additionally, the presence of a central bar can help maintain spiral structure, with the arms often emerging from the ends of the bar and extending into the outer disk. In many cases, multiple mechanisms may contribute to the spiral structure observed in a particular galaxy. The pitch angle of spiral arms, which describes how tightly wound they are, varies among galaxies. A small pitch angle indicates tightly wound arms that make many revolutions before reaching the outer edge of the disk, while a large pitch angle indicates more open arms that make fewer revolutions. The pitch angle appears to correlate with other galactic properties, with early type spirals generally showing smaller pitch angles and later type spirals showing larger ones. In the Milky Way, the pitch angle is estimated to be around 12 to 15 degrees, creating moderately wound spiral arms. Observations in different wavelengths reveal different aspects of spiral arm structure. In visible light, the spiral arms stand out due to the luminous young stars they contain. In infrared wavelengths, the overall stellar distribution becomes more apparent, and the arms appear less prominent because infrared light better traces the older stellar population that is more evenly distributed throughout the disk. Radio observations of neutral hydrogen and molecular gas show that gas concentrations follow the spiral arms closely, as expected if the arms represent density enhancements that compress gas and trigger star formation. Ultraviolet observations emphasize the youngest, hottest stars even more strongly than visible light, making the spiral pattern particularly stark in UV images. The spacing between spiral arms depends on the number of arms and the size of the galaxy. In a two-armed grand design spiral, the arms may be separated by roughly 180 degrees, creating a symmetric pattern that persists over large portions of the visible disk. In galaxies with more arms or more fragmentary spiral structure, the spacing becomes less regular, with arms beginning and ending at various distances from the center and sometimes bifurcating or merging. The Milky Way appears to have several spiral arms with varying degrees of prominence, creating a structure more complex than a simple two-armed pattern, but not as fragmentary as the most flocculent spirals. The dust lanes visible along the inner edges of spiral arms in many galaxies represent the compressed gas that has not yet formed stars. As gas flows into the spiral arm, it encounters a shock front where it is compressed and slowed. This compressed gas appears dark in visible light because the dust mixed with the gas absorbs and scatters starlight. Behind the dust lane, newly formed stars begin to emerge, their light gradually dispersing the remaining gas and dust through radiation pressure and stellar winds. This progression from dust lane to newly formed stars to more evolved stellar population creates a structure within each spiral arm, with different stages of star formation visible at different positions relative to the arm's leading edge. The gravitational potential created by a spiral arm can be modeled mathematically using perturbation theory, treating the arm as a relatively small deviation from an axis-symmetric disk. These models predict that material should orbit the galaxy slightly more slowly within the arms than between them, due to the additional gravitational force from the enhanced density. Observations of gas kinematics generally confirm these predictions, showing that gas does slow down as it enters spiral arms, though the details vary from galaxy to galaxy depending on the strength of the spiral pattern and other factors. The self-gravity of the spiral pattern itself helps to maintain the structure over time. The enhanced density in the arms creates additional gravitational forces that act back on the rest of the disk, helping to prevent the spiral pattern from dissipating too quickly. This self-reinforcing nature means that once a spiral pattern forms, it can persist for many galactic rotations, gradually evolving but not rapidly disappearing. Computer simulations of disk galaxies confirm that spiral patterns can be long-lived features lasting for several billion years in many cases. Spiral arms also affect the chemistry of the interstellar medium by cycling material through repeated episodes of star formation and enrichment. Gas enters an arm, forms stars, and those stars eventually die and return enriched material to the interstellar medium through stellar winds and supernovae. This processed material then drifts out of the arm and eventually re-enters another arm downstream, where it participates in another round of star formation. Over billions of years, this cycling gradually increases the overall metallicity of the disk, though the effect is gradual because much of the gas remains in the disk rather than being incorporated into long-lived stars. The study of spiral arms in external galaxies benefits from the face-on perspective that allows us to trace the full extent of the spiral pattern across the disk. In our own Milky Way, determining the spiral structure requires piecing together observations from our position within the disk, a task complicated by dust obscuration and the limited range over which we can accurately measure distances to individual objects. Nevertheless, observations of young star clusters, molecular clouds, and regions of ionized hydrogen have revealed the basic spiral structure of the Milky Way, confirming that we inhabit a galaxy with multiple spiral arms radiating from a central bar. The formation of new stars in spiral arms contributes to the chemical evolution of the galaxy by producing heavy elements that are later dispersed into the interstellar medium. Massive stars, which form preferentially in the high-density environments of spiral arms, synthesize elements up to iron through nuclear fusion during their lifetimes and produce even heavier elements in their supernova explosions. These elements become incorporated into later generations of stars, creating a pattern where younger stars tend to be more metal-rich than older stars. This chemical gradient is visible in the stellar populations of spiral galaxies, with halo stars showing low metallicities and young disk stars showing metallicities comparable to or exceeding that of the Sun. The visual beauty of spiral galaxies, which makes them popular subjects for astronomical imaging, arises largely from the contrast between the bright spiral arms and the dimmer inter-arm regions. This contrast exists not because the inter-arm regions lack stars, but rather because they lack the luminous young stars that dominate the light from spiral arms. When observed in infrared wavelengths, which better trace the older stellar population, the inter-arm regions appear brighter and the spiral pattern less striking. This wavelength dependence demonstrates that the spiral pattern we see in visible light primarily reflects the distribution of star-forming regions rather than the underlying distribution of stellar mass. Spiral arms thus represent a beautiful example of how gravitational forces, gas dynamics, and star formation interact to create persistent patterns in rotating disk systems. The arms are neither permanent concentrations of stars nor transient phenomena that quickly disperse, but rather long-lived density waves that organize star formation and create the characteristic appearance that defines spiral galaxies. Understanding this architecture requires recognizing that what we see is a pattern maintained by the continuous flow of material through rotating density enhancements, not a static structure composed of fixed groups of stars. The colors visible in spiral galaxies reveal fundamental information about the ages and types of stars in different regions. Blue light indicates the presence of hot, young stars with surface temperatures exceeding 10,000 Kelvin, while red or yellow light typically comes from cooler, older stars with temperatures around 4,000 to 6,000 Kelvin. The striking contrast between blue spiral arms and red or yellow bulges visible in many face-on spiral galaxies directly reflects this difference in stellar populations. Young stars appear blue because their high surface temperatures cause them to emit most of their light at shorter wavelengths in the blue and ultraviolet portions of the spectrum. These stars form from the collapse of molecular clouds in the spiral arms, where gas densities are high enough to trigger gravitational collapse. The most massive of these newborn stars, classified as O and B spectral types, have masses ranging from 10 to perhaps 100 times the mass of the Sun. Their tremendous luminosities, up to 1 million times that of the Sun, mean that a handful of such stars can outshine millions of older, less massive stars. However, massive stars burn through their nuclear fuel rapidly due to their high core temperatures and pressures. A star of 60 solar masses might exhaust its hydrogen supply in only 3 million years, while a star of 20 solar masses lasts perhaps 10 million years. After exhausting their core hydrogen, these massive stars expand into supergiants, their outer layers swelling to enormous sizes while their cores continue fusing heavier elements in successive shells. The end comes quickly in the form of a supernova explosion that disperses much of the star's mass into the surrounding interstellar medium while leaving behind either a neutron star or a black hole. This rapid evolution means that massive blue stars are excellent tracers of recent star formation. Their presence indicates that molecular clouds collapsed into stars within the past few million to perhaps 10 million years, an eye blink in cosmic time. The concentration of these young stars in spiral arms demonstrates that active star formation occurs preferentially in the arms, where density enhancements compress gas to the point where gravitational collapse becomes likely. The absence of such stars in the inter-arm regions does not mean those regions lack stars entirely, but rather that they lack stars young enough to still be in their short-lived, luminous blue phase. The central bulges of spiral galaxies show red or yellow colors because they contain primarily older stars that formed billions of years ago during the early assembly of the galaxy. These stars have lower masses, typically less than 1 solar mass, and have survived for billions of years, while more massive stars in the same generation lived and died long ago. The color of such stars shifts toward the red as they age and evolve off the main sequence, with many becoming red giants whose outer layers have expanded and cooled. The integrated light from billions of these red and yellow stars gives bulges their characteristic warm hues. Population 1 stars, found primarily in the disk, are relatively young and metal-rich, having formed from gas already enriched with heavy elements from previous stellar generations. Population 2 stars, found in the bulge and halo, are older and metal-poor, having formed earlier when the interstellar medium contained fewer heavy elements. This population distinction correlates with color, as Population 1 regions tend to appear bluer due to ongoing star formation, while Population 2 regions appear redder due to the predominance of old, evolved stars. The presence of both populations in a single galaxy creates the color gradients visible in high-quality images of spiral systems. Dust also affects the observed colors of spiral galaxies by preferentially absorbing and scattering blue light while allowing red light to pass through more easily. This reddening effect can make dust-rich regions appear redder than they would in the absence of dust, potentially confusing the interpretation of colors as indicators of stellar age. Astronomers must correct for this dust reddening by measuring the amount of extinction and calculating what the intrinsic colors of stars would be in the absence of dust. Infrared observations, which are less affected by dust, provide crucial information for determining true stellar populations in dust-obscured regions. The blue colors of spiral arms can fade relatively quickly on cosmic timescales if star formation ceases in a region. Once the short-lived massive stars die, only the longer-lived, less luminous stars remain, causing the region to appear redder. This process, called passive evolution, occurs in regions where gas has been depleted or blown away by stellar winds and supernovae, preventing new star formation. Some spiral galaxies show evidence of color gradients in their arms, with the arms appearing bluer near the galactic center, where star formation is most active, and redder in the outer disk where gas densities are lower and star formation less frequent. The color of a galaxy as a whole depends on the balance between star formation in the disk and the older stellar population in the bulge and halo. Late-type spirals with small bulges and active star formation appear quite blue in integrated light, while early-type spirals with large bulges and less active star formation appear yellower or redder. This color morphology relationship allows astronomers to estimate the star formation activity in distant galaxies where individual regions cannot be resolved, using the integrated color as a proxy for the average stellar age and star formation rate. Spectroscopic observations provide more detailed information about stellar populations than broadband colors alone. By measuring the strengths of various absorption lines in the integrated light from a galaxy, astronomers can determine the abundances of different elements and estimate the ages of stellar populations. Strong hydrogen absorption lines indicate the presence of intermediate temperature stars, while strong metal lines suggest metal-rich populations. Emission lines from ionized gas reveal ongoing star formation as hot young stars ionize the surrounding gas and cause it to emit characteristic wavelengths. The study of colors in spiral galaxies has revealed that many nearby spirals contain stellar populations spanning a wide range of ages, from 10 billion years for the oldest stars in the bulge and halo, to just a few million years for the youngest stars in active star-forming regions. This extended star formation history means that these galaxies have continuously produced new stars throughout their lifetimes, though the rate has likely varied over time in response to factors like gas accretion, mergers with satellite galaxies, and internal dynamical processes. The persistence of star formation over such long timescales requires either that the galaxy retain substantial gas reservoirs or that it continue to accrete fresh gas from the intergalactic medium. Color gradients within individual spiral arms can be detected in nearby galaxies where spatial resolution is sufficient to separate different parts of the arms. These gradients often show the youngest stars nearest the spiral arm's leading edge, where gas compression is strongest and star formation most active. Slightly older stars appear downstream along the arm, having had time to drift somewhat from their birthplaces. The most evolved regions, where the initial burst of star formation has ceased and the most massive stars have already died, appear redder and less luminous. This progression creates a kind of age sequence visible along the length of spiral arms in high-resolution images. The colors of spiral galaxies also provide clues about their chemical evolution over cosmic time. The metallicities of stars correlate with their ages, with older stars generally showing lower metallicities. This pattern arises because successive generations of stars enrich the interstellar medium with heavy elements, causing later generations to form from gas with higher metal content. The Anchur color metallicity relationship means that red, old stars tend to have low metallicities, while blue, young stars have higher metallicities, though this relationship is not perfect because stellar evolution also affects color independently of metallicity. Understanding the colors of spiral galaxies requires integrating information about stellar evolution, star formation, chemical enrichment, dust extinction, and stellar population synthesis. The observed colors result from the combined light of billions of individual stars, each with its own temperature, luminosity, and composition, summed over the entire visible portion of the galaxy. Modern techniques of population synthesis modeling allow astronomers to decompose this integrated light into contributions from different stellar populations, recovering estimates of star formation history, metallicity evolution, and other properties that are not directly observable. These analyses have confirmed that spiral galaxies are indeed complex systems with extended star formation histories and multiple stellar populations coexisting in different spatial regions. The creation of new stars occurs primarily in the spiral arms of disk galaxies, where molecular gas reaches densities high enough to overcome internal pressure and collapse under its own gravity. The process begins with giant molecular clouds, regions of cold molecular hydrogen extending tens to hundreds of light years and containing thousands to millions of solar masses of material. These clouds exist throughout the galactic disk, but their properties and star-forming efficiency vary with position, being generally higher in spiral arms where density wave compression enhances the overall gas density. Within a giant molecular cloud, even denser regions called molecular cores contain most of the mass that will eventually form individual stars or small stellar groups. These cores have densities exceeding 10,000 hydrogen molecules per cubic centimeter, several orders of magnitude higher than the average interstellar density. At such densities, hydrogen molecules can cool efficiently through rotational and vibrational transitions, removing thermal energy and allowing the core to contract further under gravity. Once the core begins collapsing, the process accelerates as gravitational forces increase and gas falls inward. The timescale for star formation within a molecular cloud is surprisingly short compared to galactic rotation periods. Observations of nearby star-forming regions suggest that molecular clouds convert their gas into stars over timescales of 10 to 30 million years, then dissipate through the combined effects of stellar winds, radiation pressure from newly formed stars, and supernova explosions from the most massive stars. This rapid cycling means that the molecular clouds visible in a spiral arm today will have largely dispersed within one galactic rotation period, to be replaced by new clouds formed from gas compressed in later passages through the arms. The rate at which a galaxy forms stars depends on the amount of molecular gas available and the efficiency with which that gas is converted into stars. The Milky Way currently forms approximately 2 solar masses worth of new stars each year, averaged over the entire galaxy. This rate has likely varied over the galaxy's history, being higher in the early universe when more gas was available and possibly during periods of enhanced gas accretion or merger activity. The star formation rate can be estimated observationally by counting young stars or by measuring the luminosity in ultraviolet or infrared wavelengths that trace recent star formation. The initial mass function describes the distribution of stellar masses formed from a collapsing molecular cloud. Observations indicate that for every high-mass star formed, many more low-mass stars also form, with the number of stars increasing steeply toward lower masses. This means that most stars by number have masses less than 1 solar mass, even though massive stars dominate the total light output during their lifetimes. The initial mass function appears to be relatively universal across different star-forming environments, suggesting that the fundamental physics of fragmentation and collapse operates similarly regardless of location. Massive stars, despite being rare compared to low-mass stars, have an outsized influence on their surroundings. A single O-type star emits enough ultraviolet radiation to ionize hydrogen throughout a region hundreds of light years across, creating an H2 region that glows with characteristic red light from hydrogen recombination. Multiple O-stars in a young cluster can create even larger ionized regions, visible as bright nebulae in images of nearby star-forming galaxies. These H2 regions serve as beacons marking sites of very recent star formation as they fade within a few million years after the death of the massive stars that ionize them. The energy input from massive stars eventually disrupts the molecular cloud that formed them, a process called feedback. Stellar winds from hot young stars sweep out cavities in the surrounding gas, while supernova explosions inject tremendous amounts of energy and momentum. This feedback can both suppress and trigger star formation, suppressing it by dispersing and heating gas that might otherwise collapse, while triggering it by compressing gas at the edges of expanding bubbles. The net effect is to regulate the star formation rate, preventing molecular clouds from converting all their gas into stars too efficiently. Observations with radio telescopes allow astronomers to map the distribution of molecular gas in spiral galaxies through emission from carbon monoxide molecules, which serve as a tracer for molecular hydrogen. These observations reveal that molecular gas concentrates in spiral arms, as expected from density wave theory, with surface densities in the arms exceeding those in inter-arm regions by factors of 2 to 5. The enhanced gas density correlates with increased star formation rates, confirming that the compression of gas in spiral arms drives the elevated star formation that makes the arms appear bright. The timescale for gas to pass through a spiral arm depends on the pattern speed of the spiral density wave and the orbital velocity of the gas at that radius. In the Milky Way, gas typically takes several tens of millions of years to cross through a spiral arm, during which time molecular clouds can form, produce stars, and begin to disperse due to feedback from those stars. This means that a single parcel of gas experiences multiple cycles of arm passage during one galactic orbit, with star formation potentially occurring during each passage through an arm, though the timing and efficiency may vary. The spatial correlation between molecular gas and young stars provides strong evidence that spiral arms trigger star formation through density wave compression. High-resolution observations of nearby galaxies reveal that the youngest stars lie on the inner edges of spiral arms, just downstream from the locations of peak molecular gas density. Slightly older stellar populations appear farther downstream, having had time to drift away from their birthplaces. This age gradient along spiral arms demonstrates the sequential nature of star formation driven by the passage of gas through density enhancements. Star formation also occurs in the inter-arm regions of spiral galaxies, though at lower rates than in the arms. Some molecular clouds may form between arms through local gravitational instabilities, or fragments of clouds dispersed from arms may survive long enough to form stars before completely dissipating. The ratio of arm to inter-arm star formation varies among galaxies, with grand design spirals showing strong concentration of star formation in the arms and flocculent spirals showing more distributed star formation. This variation suggests that the strength of the spiral density wave influences how efficiently star formation is concentrated in spiral arms. The chemical evolution of spiral galaxies depends critically on star formation, because stars produce heavy elements through nuclear fusion and distribute those elements through stellar winds and supernova explosions. Each generation of stars increases the metallicity of the interstellar medium, causing later generations to form from gas with higher abundances of elements heavier than helium. The metallicity of the interstellar medium in spiral galaxies today typically ranges from about 50% to twice the solar metallicity, depending on the galaxy and location within it, with inner regions generally being more metal-rich than outer regions. The study of star formation in external galaxies complements detailed studies of nearby star-forming regions within the Milky Way. While observations within our galaxy provide exquisite detail about individual molecular cores, protostars, and young stellar clusters, external galaxies allow us to see star formation patterns in different environments and to study how star formation relates to large-scale galactic structure. Combining these perspectives has revealed that star formation is a complex process involving gravity, gas dynamics, magnetic fields, turbulence, and stellar feedback operating on scales from individual protostars to entire galactic disks. Modern theoretical models of star formation attempt to capture this complexity through hydrodynamic simulations that follow the evolution of gas from large-scale cloud formation through collapse into individual stars. These simulations must include the effects of turbulence, magnetic fields, radiation transport, and stellar feedback to achieve realistic results. When successful, they reproduce many observed features of star formation, including the initial mass function, the efficiency with which clouds convert gas into stars, and the spatial distribution of young stars in spiral arms. However, significant uncertainties remain, particularly regarding how feedback operates on small scales and how magnetic fields affect cloud collapse. Spiral galaxies rotate as coherent systems, with stars and gas orbiting the galactic center in paths determined by the gravitational potential of the entire galaxy. The rotation is differential, meaning that different radii rotate at different angular velocities rather than the galaxy spinning like a solid body. This differential rotation arises naturally from the distribution of mass throughout the galaxy, with the gravitational force on a star depending on its distance from the center and the amount of mass interior to its orbit. The velocity of stars orbiting the galactic center typically ranges from 100 to several hundred kilometers per second, depending on their distance from the center and the total mass of the galaxy. In the Milky Way, stars near the Sun's position orbit at approximately 230 kilometers per second. This velocity remains roughly constant across a wide range of radii in the outer parts of the galaxy, creating what astronomers call a flat rotation curve. The flatness of rotation curves in spiral galaxies provided some of the earliest evidence for dark matter, as the observed velocities exceed what would be expected from the gravitational pull of visible matter alone. The orbital period of a star around the galactic center depends on its distance from the center and its velocity. A star at 8 kiloparsecs from the center, like the Sun, with a velocity of 230 kilometers per second, requires approximately 225 million years to complete one orbit. This timescale, sometimes called a galactic year or cosmic year, provides a natural unit for measuring cosmic time. Since the Sun formed roughly 4.5 billion years ago, it has completed approximately 20 orbits around the galactic center during its lifetime. The motion of stars through the disk is not perfectly circular, but rather slightly elliptical, with small deviations from perfect circular motion called peculiar velocities. These peculiar velocities typically amount to tens of kilometers per second, much smaller than the overall orbital velocity, but significant enough to cause stars to move in and out from the galactic center as they orbit. The Sun's peculiar velocity carries it through the galactic midplane roughly every 60 million years, causing it to oscillate above and below the plane while maintaining its overall orbital motion around the center. Density waves in the spiral arms rotate at a pattern speed that differs from the orbital speeds of stars and gas. This difference means that stars continually enter and leave spiral arms during their orbits, spending only a fraction of each orbital period within a given arm. The corrotation radius marks the location where the pattern speed equals the orbital speed, so that material at this radius maintains a constant angular relationship to the spiral pattern. Inside this radius, stars overtake the spiral pattern, while outside it, the pattern overtakes the stars. The concept of a galactic year provides a useful framework for placing terrestrial events in cosmic context. 225 million years ago, when the Sun was in roughly the same position in its orbit as today, the Earth was in the Triassic period, with dinosaurs just beginning to emerge. One galactic year before that, during the Carboniferous period, vast coal swamps covered much of the land. The entire history of complex multicellular life on Earth spans roughly 3 galactic years, while the age of the universe encompasses about 60 galactic years since the Big Bang. These comparisons illustrate how galactic timescales relate to more familiar terrestrial timescales. Dark matter plays a crucial role in determining rotation, curves, and orbital velocities in spiral galaxies. The flat rotation curves observed in most spirals require that mass continues to increase linearly with radius well beyond the visible edge of the galaxy, a pattern inconsistent with the exponentially declining surface brightness of visible stars. Theoretical models place most of this dark matter in an extended spherical or ellipsoidal halo surrounding the visible galaxy, with the dark matter density declining gradually with distance from the center but remaining significant even at large radii. The total mass of a spiral galaxy can be estimated from its rotation curve using a generalization of Kepler's third law. The orbital velocity at a given radius provides a measure of the gravitational force at that location, which depends on the total mass interior to that radius. By measuring velocities at many different radii, astronomers can construct a mass profile showing how mass is distributed throughout the galaxy. For the Milky Way, such analyses suggest a total mass of roughly 1 trillion solar masses within a radius of 200 kiloparsecs, though much of this mass is dark matter rather than visible stars and gas. Stars born at different distances from the galactic center maintain roughly those distances throughout their lifetimes, though radial migration can cause some stars to drift inward or outward over billions of years. This migration occurs through gravitational interactions with spiral density waves and other non-axisymmetric features that can change a star's angular momentum. Nevertheless, the overall radial distribution of stars remains fairly stable over time, with most stars staying relatively close to their birth radii. This stability helps preserve chemical gradients in the disk, as stars born in the metal-rich inner galaxy remain generally inward of stars born in the outer galaxy. The rotation of a spiral galaxy can be measured observationally through spectroscopy of stars or gas throughout the disk. When observing a galaxy edge-on, light from the side rotating toward us is blue-shifted due to the Doppler effect, while light from the side rotating away is red-shifted. The magnitude of these shifts reveals the rotation velocity at each position in the galaxy. For face-on galaxies, this technique does not work because the rotation is perpendicular to our line of sight, but other methods based on proper motions or statistical analysis of stellar populations can still provide information about rotation. The relationship between rotation speed and galaxy mass provides a useful tool for studying galaxy evolution. More massive galaxies generally rotate faster, following an empirical relationship called the Tully-Fisher relation. This relationship allows astronomers to estimate distances to spiral galaxies by measuring their rotation speeds and comparing the apparent brightness with the expected intrinsic brightness for a galaxy of that mass. The reliability of this method has made it an important tool in cosmology for measuring distances to galaxies too far away for other techniques to work effectively. Rotation curves also reveal information about the detailed mass distribution within galaxies. Galaxies with prominent bars show characteristic velocity patterns near the bar, with gas streaming along the bar toward the center. Spiral arms create smaller scale variations in rotation velocities as gas flows through the density enhancements. By carefully modeling these deviations from simple circular motion, astronomers can map out the three-dimensional distribution of mass in spiral galaxies and understand how bars and spirals affect gas dynamics. The stability of galactic disks against gravitational perturbations depends on the balance between rotational support and gravitational forces. A disk with insufficient random velocity dispersion can become unstable to gravitational collapse, forming spiral structure or breaking up into clumps. However, too much random motion prevents coherent spiral patterns from forming. The disks of spiral galaxies appear to occupy a regime where they are stable enough to avoid fragmentation, but unstable enough to develop spiral structure, creating the patterns we observe. This delicate balance has been maintained for billions of years in many spiral galaxies. The motion of individual stars through the galaxy is complex, combining circular motion around the galactic center with epicyclic oscillations in and out from the mean orbit and vertical oscillations above and below the midplane. The epicyclic frequency determines how quickly a star moves in and out from its mean radius, while the vertical oscillation frequency determines how often it crosses the midplane. These three characteristic frequencies, rotation, epicyclic, and vertical, together define the complete orbital motion of a star in the galactic potential. Understanding this motion allows astronomers to predict where stars will be at any given time and to trace their paths through the galaxy over long timescales. Spiral galaxies span a remarkable range of sizes, from dwarf spirals a few thousand light-years across to giant spirals exceeding 300,000 light-years in diameter. The Milky Way, with its approximately 100,000 light-year diameter, falls near the middle of this range, being neither particularly large nor particularly small compared to other spiral galaxies in the universe. Understanding these scales requires grappling with distances that dwarf anything familiar from terrestrial experience or even solar system exploration. A light year represents the distance light travels in 1 year at its constant speed of 300,000 kilometers per second, approximately 9.5 trillion kilometers or 6 trillion miles. Even at this tremendous scale, galaxies are so large that their dimensions must be expressed in tens or hundreds of thousands of light years. The Milky Way's diameter of 100,000 light years means that light from one edge of the galaxy requires 100,000 years to reach the opposite edge, traveling continuously at its maximum possible speed through the vacuum of space. Within the Milky Way, the Sun lies approximately 26,000 light-years from the galactic center, roughly 1/4 of the way from the center to the outer edge. This places our solar system in what might be called the galactic suburbs, far from the dense central bulge, but not in the outermost reaches of the disk. From this position, we look inward toward the galactic center when observing the constellation Sagittarius, and outward toward the galaxy's edge when observing in the opposite direction. The entire visible band of the Milky Way stretching across Earth's night sky represents our view along the plane of the galactic disk from our location within it. The scale height of the galactic disk, approximately 1,000 light-years near, the Sun's position represents the vertical extent of most stars above and below the midplane. This thickness is tiny compared to the disk's diameter, giving the disk an aspect ratio similar to that of a compact disc or vinyl record. Most stars remain within a few hundred light-years of the midplane throughout their orbits, creating the flattened structure visible when we observe spiral galaxies edge-on from other galaxies. The thin disk component, containing the youngest stars and most gas, has an even smaller scale height of only a few hundred light-years. The central bulge of the Milky Way extends roughly 10,000 light-years from the galactic center, appearing as a roughly spherical or bar-shaped concentration of old stars. This region contains densely packed stars with typical separations of a few light-years, much closer than the typical 5 light-year separation between stars in the Sun's neighborhood. The stellar density in the very center, within the innermost parsec, reaches even more extreme values, with stars separated by only small fractions of a light-year. Such crowding makes the inner bulge a very different environment from the galactic suburbs where we reside. The galactic halo extends well beyond the visible disk, with globular clusters and individual halo stars found at distances of several 100,000 light-years from the galactic center. The dark matter halo extends even farther, possibly to distances exceeding 500,000 light-years. This means that the true extent of the Milky Way, including its dark matter content, is several times larger than the visible stellar disk. The gravitational influence of the galaxy extends outward until it is overwhelmed by the gravitational pull of neighboring galaxies in the local group. Measuring distances to other spiral galaxies requires indirect techniques because we cannot physically travel to them or measure their distances using geometric methods like parallax. For nearby galaxies within a few tens of millions of light-years, astronomers can identify individual stars called Cepheid variables, whose intrinsic brightnesses are known from their pulsation periods. By comparing the apparent brightness of these stars with their known intrinsic brightness, the distance can be calculated using the inverse square law of light. The Hubble Space Telescope has measured Cepheids in dozens of nearby galaxies, establishing a distance scale for the local universe. The Andromeda Galaxy, our nearest large spiral neighbor, lies approximately 2.5 million light-years away. This means the light we observe from Andromeda left that galaxy 2.5 million years ago, during the Pliocene epoch on Earth when early human ancestors were walking in Africa. The Triangulum Galaxy, another member of our local group, sits at roughly 3 million light-years distance. These two galaxies, along with the Milky Way, constitute the three major spiral galaxies in our immediate cosmic neighborhood, surrounded by dozens of smaller dwarf galaxies. At larger distances, individual stars become impossible to resolve even with the most powerful telescopes, and distance measurements must rely on other indicators. Type 1. A supernovae serve as excellent distance markers because their peak brightness is remarkably uniform, allowing them to be used as standard candles for measuring distances out to billions of light-years. The relationship between galaxy rotation speed and luminosity, called the Tully-Fisher relation, provides another distance estimation method for spiral galaxies where rotation curves can be measured. Combining multiple techniques allows astronomers to build up a distance ladder extending from nearby galaxies to the edge of the observable universe. The largest known spiral galaxies extend several 100,000 light-years across their visible disks. NGC 6872, for example, spans approximately 522,000 light-years from one end of its outstretched spiral arms to the other, making it roughly 5 times the diameter of the Milky Way. Such giant spirals are rare but not unique, with a few dozen examples known from deep surveys of the nearby universe. Their formation likely involved mergers with other large galaxies or unusually efficient accretion of gas during the galaxy's early history. At the other extreme, dwarf spiral galaxies may be only a few thousand light-years across, containing just a few billion stars compared to the hundreds of billions in large spirals. These small systems blur the distinction between spiral galaxies and irregular galaxies, often showing only fragmentary spiral structure or loosely organized arms. Despite their small size, dwarf spirals provide important clues about galaxy formation because they represent less evolved systems where star formation may still be actively shaping the galactic structure. The volume of space occupied by a spiral galaxy depends on both its diameter and thickness. For a typical disk galaxy 100,000 light-years in diameter and 1,000 light-years thick, the volume is approximately 8 billion cubic light-years, though most of this volume is nearly empty space with densities far below those of even the best terrestrial laboratory vacuums. The average density of matter in a galactic disk is roughly 1 hydrogen atom per cubic centimeter, with most of the mass concentrated in stars that occupy only a tiny fraction of the total volume. Traversing even a modest galaxy at the speed of light would require 100,000 years, highlighting how empty and vast these structures truly are, despite containing hundreds of billions of stars. At the velocity of current spacecraft, roughly tens of kilometers per second, crossing a galaxy would take hundreds of millions of years. No human technology could travel between galaxies in any reasonable timescale, and even signals sent at the speed of light would take millions of years to traverse intergalactic distances. These realities enforce a kind of cosmic isolation, with each galaxy effectively a separate island in an ocean of intergalactic space. The observable universe contains billions of spiral galaxies, each separated from its neighbors by millions of light-years on average. The total number of spiral galaxies in the observable universe likely exceeds 100 billion, though exact counts are difficult because many distant galaxies are too faint to detect, and because galaxy classification becomes ambiguous for very distant, young galaxies whose morphology differs from that of nearby, mature systems. Every one of these billions of spiral galaxies represents a system comparable in complexity to the Milky Way, containing its own populations of stars, gas clouds, stellar nurseries, and likely countless planetary systems. At the heart of nearly every large spiral galaxy lies a supermassive black hole, an object containing millions to billions of times the mass of the Sun compressed into a volume smaller than our solar system. These black holes exert tremendous gravitational forces on nearby matter, but represent only a small fraction of the total mass of their host galaxies. The black hole at the center of the Milky Way, designated Sagittarius A star, contains approximately 4 million solar masses within a region whose size can be estimated at roughly 17 light-hours, or about 120 astronomical units. This central black hole was inferred from observations of stars orbiting the galactic center at tremendous velocities. Individual stars have been tracked for decades as they follow elliptical orbits around an invisible massive object. One star, designated S2, orbits with a period of approximately 16 years, reaching velocities exceeding 5,000 kilometers per second at closest approach to the black hole. The orbital parameters of S2 and other stars in the galactic center allow precise determination of the black hole's mass and location, confirming that Sagittarius A star is indeed a supermassive black hole. In 2022, the Event Horizon Telescope collaboration released the first image of Sagittarius A star, showing the shadow of the black hole surrounded by a glowing ring of hot gas. This image, produced by combining observations from radio telescopes around the world to create an Earth-sized virtual telescope, provided direct visual confirmation of the black hole's existence and properties. The ring of emission comes from gas orbiting just outside the event horizon, heated to billions of degrees by friction and magnetic fields as it spirals inward toward the black hole. The event horizon of Sagittarius A star, the boundary beyond which nothing can escape, has a radius of approximately 12 million kilometers, or about 17 times the radius of the Sun. Despite the black hole's enormous mass, this physical size is quite small compared to astronomical distances, explaining why the black hole's gravitational influence is dominant only in the innermost regions of the galaxy. Stars orbiting at the Sun's distance of 26,000 light-years are virtually unaffected by the black hole's gravity, responding instead to the collective gravitational pull of all the matter interior to their orbits. Supermassive black holes likely formed in the early universe through processes that remain debated among astronomers. They may have grown from smaller black holes left by the first generation of massive stars, accreting matter over billions of years until reaching their current masses. Alternatively, they might have formed more directly through the collapse of massive gas clouds in the early universe. Observations of quasars at high redshifts, corresponding to when the universe was less than 1 billion years old, indicate that supermassive black holes exceeding 1 billion solar masses already existed at those early times, suggesting rapid growth mechanisms operated in the young universe. The relationship between black hole mass and the properties of the host galaxy bulge suggests a connection between black hole growth and galaxy formation. More massive bulges tend to harbor more massive black holes, following an empirical relationship called the M-sigma relation, where black hole mass correlates with the velocity dispersion of stars in the bulge. This relationship implies that black holes and their host galaxies co-evolved, with the growth of each somehow linked to the other. The mechanisms behind this coevolution remain an active area of research, possibly involving feedback where energy released by gas accreting onto the black hole affects star formation throughout the galaxy. Most supermassive black holes in nearby spiral galaxies are relatively quiescent, accreting matter at low rates and producing minimal radiation. Sagittarius A star, for example, accretes gas at a rate that converts only a tiny fraction of the infalling matter's rest mass into radiation, making it one of the faintest supermassive black holes despite its proximity to Earth. This quiescence suggests that black holes spend most of their time in a dormant state, occasionally flaring to higher luminosities when a star wanders too close and is tidally disrupted, or when a substantial amount of gas reaches the immediate vicinity of the black hole. Active galactic nuclei represent the opposite extreme, where supermassive black holes accrete matter at high rates and produce tremendous luminosities exceeding that of all the stars in the host galaxy combined. These active systems appear most common at high redshifts, corresponding to earlier cosmic times when gas was more abundant and galaxy mergers more frequent. In the local universe, only a small fraction of galaxies show strong nuclear activity, suggesting that most supermassive black holes have entered a quiescent phase after consuming or expelling most of the available gas in their immediate surroundings. The bulge surrounding the central black hole in spiral galaxies consists primarily of old stars formed billions of years ago. These stars have low metallicities compared to younger disk stars, indicating they formed early in the galaxy's history before the interstellar medium had been substantially enriched with heavy elements. The bulge population is sometimes called Population 2, distinguishing it from the younger Population 1 stars in the disk. The kinematics of bulge stars differ from disk stars, with bulge stars showing more random motion and less coherent rotation, suggesting different formation mechanisms or evolutionary histories. Some spiral galaxies show evidence of recent star formation even in their bulges, particularly in barred spirals where the bar can funnel gas toward the center. This gas accumulates in the inner few hundred parsecs, forming dense molecular clouds that may collapse into new stars, despite the old age of most bulge stars. These young stars in the bulge create a mixture of stellar populations with hot blue stars embedded among the predominantly old red population. The presence of such young stars demonstrates that galactic centers remain dynamic environments even billions of years after the galaxy's formation. The inner few kiloparsecs of spiral galaxies often show a bar structure, an elongated distribution of stars extending from the central bulge. Approximately 2/3 of all spiral galaxies possess such bars, including the Milky Way, where the bar extends roughly 27,000 light-years end to end. Bars form through gravitational instabilities in the disk and can persist for billions of years once established. They affect the dynamics of gas in the inner galaxy by creating torques that remove angular momentum from gas, causing it to spiral inward toward the center, where it may fuel star formation or feed the central black hole. The coexistence of a supermassive black hole with billions of stars in close proximity creates a unique environment in galactic centers. Stars passing near the black hole experience strong tidal forces that can strip material from their outer layers or, in extreme cases, tear them completely apart. Such tidal disruption events produce brief flares of radiation as the stellar material is heated to extreme temperatures while falling toward the black hole. Observations have detected several such events, providing information about the properties of stars near galactic centers and the behavior of matter in strong gravitational fields. Roughly 2/3 of all spiral galaxies exhibit bar structures, elongated concentrations of stars extending from the central bulge through the inner disk. These bars are not static features, but rather persistent density waves in the stellar distribution, maintained by the gravitational interactions among stars and the overall shape of the gravitational potential. The Milky Way possesses a bar approximately 27,000 light-years in length and perhaps 7,000 light-years wide, though its exact dimensions remain uncertain due to our position within the galaxy and obscuration by dust. The presence or absence of a bar significantly affects the classification and properties of spiral galaxies. Edwin Hubble's original classification system divided spiral galaxies into normal spirals, designated SA, and barred spirals, designated SB, with a third category, SAB, for galaxies showing intermediate characteristics. This bar dichotomy extends throughout the Hubble sequence, with barred and unbarred variants at each stage from early type to late type spirals. Modern observations suggest that the bar phenomenon is common and that many galaxies previously classified as unbarred actually possess weak bars visible only in infrared observations that penetrate dust and better trace the older stellar population. The formation of bars represents a gravitational instability in rotating galactic disks. Under certain conditions, perturbations in the stellar distribution can grow, creating elongated patterns that rotate more slowly than the stars themselves. Once formed, bars are remarkably stable structures that can persist for billions of years, though they may strengthen or weaken in response to changes in the disk mass distribution or interactions with other galaxies. Computer simulations of disk galaxy evolution routinely produce bars, suggesting that bar formation is a natural consequence of disk dynamics rather than requiring special circumstances. Bars affect the flow of gas in the inner regions of galaxies by creating non-axisymmetric gravitational forces that transfer angular momentum from gas to stars. Gas moving through a bar experiences torques that cause it to lose angular momentum and spiral inward, accumulating in the central few hundred parsecs. This gas pileup can fuel enhanced star formation in nuclear rings or feed the central supermassive black hole, potentially triggering active galactic nucleus activity. The efficiency of gas transport depends on the strength of the bar, with stronger bars producing more dramatic effects on gas dynamics. Grand design spiral galaxies possess prominent, symmetric spiral arms that extend coherently across much of the visible disk. These galaxies typically show two primary arms emerging from a central bar or bulge and maintaining their identity over large radial distances. The spiral pattern in grand design systems appears particularly regular and striking in face-on views, making these galaxies popular subjects for astronomical imaging. Perhaps 10 to 15% of spiral galaxies show such well-defined grand design patterns, with the most famous examples including M51, the Whirlpool Galaxy, and M81. The regularity of grand design spirals suggests that their spiral structure arises from long-lived density waves rather than transient features or star formation feedback. In some cases, the presence of a companion galaxy provides a clear trigger for the spiral pattern, with tidal forces from the companion galaxy driving the density waves that create the arms. M51 displays such a companion interaction with the smaller galaxy NGC 5195 appearing to pull material from M51's disk. However, many grand design spirals lack obvious companions, indicating that internal gravitational instabilities can also generate persistent spiral patterns. Flocculent spiral galaxies represent the opposite extreme from grand design systems, showing multiple fragmentary spiral arms that lack the coherence and symmetry of grand design patterns. These galaxies may have dozens of short arm segments, giving the spiral structure a patchy or clumped appearance. The arms often begin and end at various distances from the center, creating an overall pattern that appears more chaotic than the smooth, symmetric spirals of grand design systems. Perhaps 60 to 70% of spiral galaxies show flocculent characteristics to varying degrees. The spiral structure in flocculent galaxies likely arises from a combination of local gravitational instabilities and star formation feedback rather than global density waves. Regions of active star formation can trigger additional star formation in adjacent areas through the compression of gas by expanding H2 regions and supernova remnants. These self-propagating star formation episodes create short-lived arms that fade as the massive stars die and the stellar population ages. The fragmentary nature of flocculent spirals suggests that coherent global spiral patterns are not always maintained in disk galaxies, particularly in later type systems with less massive bulges. Intermediate spiral galaxies, designated SAB in the Hubble system, show characteristics between normal and barred spirals. These galaxies may possess weak or short bars that do not extend far from the nucleus, or they may show oval distortions rather than linear bars. The classification of such systems can be somewhat subjective, depending on the depth and wavelength of observations and the perspective from which the galaxy is viewed. This classification uncertainty reflects the reality that bars and ovals represent a continuum of structure rather than discrete categories. The evolution of spiral structure over cosmic time remains an area of active research. Observations of distant galaxies, whose light left them billions of years ago, suggest that spiral structure was less common in the early universe. Galaxies at high redshift often appear more irregular and clumpy than nearby spirals, possibly because they were still assembling and had not yet settled into stable rotating disks. The proportion of barred spirals appears to have increased with time, from perhaps 10% 8 billion years ago to the current 2/3, suggesting that bars form preferentially in mature disk systems. The distinction between spiral galaxies and lenticular galaxies blurs in some systems that possess disks but lack obvious spiral structure and contain little gas. These lenticular or S0 galaxies may represent spiral galaxies that have exhausted or lost their gas supplies, preventing continued star formation and allowing spiral structure to fade. Alternatively, they may form through different evolutionary paths, possibly involving mergers that destroy pre-existing spiral structure while preserving the disk. The existence of S0 galaxies demonstrates that disk structure alone does not necessarily produce visible spiral arms. The diversity of spiral galaxies extends to their sizes, masses, colors, star formation rates, and environments. Some spirals are isolated systems far from other massive galaxies, while others reside in groups or clusters containing dozens or hundreds of galaxies. Environmental effects can influence spiral structure, with galaxies in dense clusters more likely to lose their gas through ram pressure stripping as they move through the hot intracluster medium. This gas loss can quench star formation and cause spiral structure to fade, potentially transforming spirals into lenticulars over time. The Hubble sequence of galaxy classification, while useful for organizing spiral galaxies by their morphological properties, does not represent an evolutionary sequence. Galaxies do not typically evolve from early type S-A spirals to late type S-C spirals, or vice versa, through normal evolutionary processes. Rather, the position on the Hubble sequence reflects the balance between bulge and disk components established during the galaxy's formation and subsequent evolution. Changes in morphological type generally require dramatic events like major mergers rather than gradual evolution. Understanding the diversity of spiral galaxies requires recognizing that these systems form through a variety of processes operating over billions of years. Gas, accretion from the intergalactic medium, mergers with smaller satellite galaxies, internal dynamical evolution, and environmental influences from neighboring galaxies all contribute to shaping the properties we observe. The spiral galaxies visible today represent snapshots of systems at various stages of this complex evolutionary process, with each galaxy's detailed history encoded in its stellar populations, chemical composition, kinematic structure, and morphology. We have traveled through the architecture of spiral galaxies, encountering the density waves that shape their arms, the stars born in molecular clouds, the colors that reveal stellar ages, the rotation that carries stars and gas around galactic centers, the vast scales that dwarf human comprehension, the supermassive black holes at galactic hearts, and the variations that give each galaxy its unique character. Throughout this journey, a recurring theme emerges. Spiral galaxies are systems of remarkable persistence and stability, maintaining their essential structures over billions of years despite continuous internal evolution. The spiral arms we observe today in nearby galaxies trace density patterns that may have existed for several billion years, surviving dozens or hundreds of galactic rotations. New stars form continuously in these arms, while older stars drift out, creating a dynamic pattern that remains visually stable even as its constituent elements change. This persistence on large scales, coexisting with constant renewal on small scales, characterizes spiral galaxies as systems in a kind of steady state, neither static nor rapidly evolving, but rather maintaining approximate equilibrium between competing processes. The billions of spiral galaxies distributed throughout the observable universe each follow similar physical laws, rotating under gravity, forming stars from molecular clouds, and evolving through the gradual consumption of gas and occasional interactions with neighboring galaxies. The universality of these processes means that insights gained from studying nearby spirals like the Milky Way and Andromeda apply broadly to spiral galaxies throughout cosmic history. The diversity we observe arises not from different fundamental physics, but from variations in initial conditions and subsequent evolutionary paths. Contemplating the scale of spiral galaxies provides a kind of perspective that transcends everyday concerns. The 100,000 light-years spanning the Milky Way represents a distance so vast that light itself, the fastest thing in the universe, requires 100,000 years to cross it. Within this volume, hundreds of billions of stars pursue their individual orbits, each potentially accompanied by planets, each contributing infinitesimally to the collective gravitational field that holds the galaxy together. The scale defies true comprehension, yet follows from straightforward applications of well-understood physical laws. The fact that we can understand spiral galaxies at all, that observations combined with theoretical models allow us to piece together their structure and evolution. Despite our inability to observe them over meaningful time spans, demonstrates the power of the scientific method applied to cosmic phenomena. Each observation, whether of stellar motions, gas distributions, colors, or structures, adds to the accumulated knowledge that forms our current picture. This picture remains incomplete and subject to revision as new observations and theoretical insights emerge, but its broad outlines appear secure. The ongoing nature of star formation in spiral galaxies means that these systems continue to evolve even in the present day. New stars form in molecular clouds compressed by density waves, live their lives, and eventually die, returning material to the interstellar medium. This cycling of material through successive generations of stars gradually enriches the gas with heavy elements and produces the chemical evolution visible in stellar populations of different ages. The process will continue for billions of years into the future until available gas supplies are exhausted or the galaxy undergoes a major merger that transforms its structure. The persistence of spiral structure over billions of years represents a kind of cosmic patience, with patterns maintained through countless rotations by the continuous operation of density waves and gravitational interactions. This persistence suggests a fundamental stability in rotating disk systems, where deviations from equilibrium are corrected by gravitational forces acting on gas and stars. The stability is not absolute. Spiral arms can strengthen or weaken, bars can form or dissolve, mergers can dramatically reorganize structure, but in the absence of major perturbations, spiral galaxies appear capable of maintaining their essential characteristics for most of cosmic history. Spiral galaxies in their multitudes populate the universe, each a gravitationally bound island containing billions of stars, vast amounts of gas and dust, and unknown numbers of planets and potentially life-bearing worlds. The processes that govern these galaxies operate continuously throughout the cosmos, forming stars, creating heavy elements, and shaping the large-scale structure of the universe. Understanding spiral galaxies provides insight into cosmic evolution and our place within the vast scale of space and time that characterizes the universe we inhabit. Thank you for spending this time exploring spiral galaxies together. These remarkable structures, with their rotating disks and elegant spiral patterns, represent some of the most visually striking and scientifically interesting objects in the observable universe. The information shared here barely scratches the surface of what astronomers have learned about these systems, and research continues to reveal new details about their formation, evolution, and properties. If you found this journey through spiral galaxy facts helpful for relaxation or sleep, consider subscribing to Nebula Nights for more content exploring astronomical topics in a calm, measured way designed to be conducive to rest. Additional videos cover other galactic types, stellar evolution, planetary systems, and various other aspects of the cosmos, all presented with the same approach of factual information delivered at a steady, unhurried pace. The like button provides a simple way to indicate that this content was valuable, helping the channel grow and reach others who might appreciate this style of astronomical exploration. Comments sharing what aspects of spiral galaxies you found most interesting or what topics you would like to see covered in future videos are always welcome and help guide the creation of new content. Until next time, whether you continue thinking about density waves and stellar populations or drift into peaceful rest, thank you for your time and attention. The spiral galaxies will continue their slow rotation through space, forming new stars and maintaining their structures across the vast scales of cosmic time.